Okay, so we're going to evaluate this infinite sum. Now our whole approach here revolves around a single trig identity, which is related to the angle sum formula for tan. So it's a matter here of spotting that we've got arctan of a fraction like this, and then recognising the following identity where if we have arctan of a certain value x and take away arctan another value y, for certain values of x and y, this is going to be equivalent to arctan of the fraction x minus y over 1 plus x times y, like this. So here this is related to, and you'll see it's a similar kind of structure to the angle sum formula for tan. And we'll actually prove this at the end and make sure that it's valid for appropriate values of x and y that we're going to use to evaluate this sum. But we can just treat this as a lemma that we're going to use to help us get started on the problem, and we'll save the proof of this till the end. So here, if we've got arctan of a fraction, we can split it up into arctan of two slightly simpler looking terms. So what we really need now is we need this root 3 over 3n squared plus 3n plus 1 term. So I'll write the 1 first, so 1 plus 3n squared plus 3n. We need this to be somehow equal to some certain values of x minus y over 1 plus xy. So we could set this up as two simultaneous equations. We essentially just want x minus y to be equivalent to root 3. Then we also want 3n squared plus 3n to be equal to x times y. So we could solve this like two simultaneous equations, get some suitable values of x and y. And a nice way of seeing how we could do this is we could actually factorise this 3n squared plus 3n term, where we take out a factor of 3n, so you get 3n goes into just n plus 1 like this. So we could try, for example, x is 3n and y is n plus 1, but you can see here x minus y then wouldn't be equal to root 3 like we want. But another way of factorising this would actually be to have root 3 with an n, and then also root 3 with an n plus 1 like this. So then if we were to say root 3 n plus 1, if we make this equal to x, and if we make root 3n equal to y, then x minus y, root 3n plus 1 minus root 3n, that is equal to root 3. And similarly you can check that x times y is indeed equal to 3n squared plus 3n, just because that's how we factorised it. So if we use these values of x and y then, where x is root 3 n plus 1 and y is root 3n, we've got our original sum with the root 3 over 3n squared plus 3n plus 1 as our x minus y over 1 plus xy. We can split this up then into arctan of x minus arctan of y. So the upshot here is then we can say that our original sum of arctan root 3 over 3n squared plus 3n plus 1, this sum is now going to be able to split this up using x and y as the sum of the arctan x minus arctan of y, where our x and y, first of all, x is root 3 n plus 1, so we can write this now just so we have it more formally. The sum from n equals 1 up to infinity of arctan x is root 3 times n plus 1. Then we take away arctan of root 3 times n for our y term. So we're taking the sum now of the differences between each of these terms, and this is now suddenly much more manageable to work with. If we look very carefully at each of the terms in this series, we'll actually see that there's a lot of cancellation now that we've got it in this new form. So if we just look at the first term where n is 1, we've got arctan of 2 root 3 minus arctan of root 3. So our first term, arctan 2 root 3 minus arctan of 1 times root 3. Then for our next term where n is 2, we get arctan of 3 root 3 minus arctan of 2 root 3. So we add in arctan 3 root 3, then when we subtract our arctan of 2 root 3, you see there's some cancellation here. Arctan 2 root 3 minus arctan 2 root 3. And similarly, when we go up to n is 3, we add in an arctan 4 root 3 term, and we take away an arctan 3 root 3 term. So here, once again, we get some cancellation. So now for this sum all the way up to infinity, it seems like there's always going to be this minus arctan root 3 term, and there's also always one left over, which also doesn't cancel. So we need to be very careful about how we approach this. So we'll actually start just by evaluating the sum from n equals 1, instead of going up to infinity, will go up to a certain value k. So we take our sum all the way up to the kth term, so we've got arctan k plus 1 times root 3 minus arctan of k root 3. So this is just going up to the term where n is equal to k. We get these terms. So here our arctan 4 root 3 term cancels with the next one, and all the way up to our minus arctan k root 3 term will cancel with the previous one, but we are left with this arctan k plus 1 root 3 term to deal with, and also this minus arctan root 3 term. So we can say then that our sum going from n equals 1 up to k is just arctan k plus 1 root 3 minus arctan root 3. And this helps us to evaluate our infinite sum now, because we essentially just define our infinite sum, so the sum from n equals 1 up to infinity. This is the limit as k goes to infinity of the partial sum from n equals 1 up to k. So then we can write this as the limit as k goes to infinity. We've just seen that the partial sum going up to the kth term is arctan of k plus 1 times root 3, then just minus arctan root 3. So these are our two terms here which don't cancel. So now all we need to do is evaluate this limit and also evaluate arctan root 3, then we'll have found the value of this infinite sum. So now to deal with taking the limit as k goes to infinity of this arctan k plus 1 root 3 term, we can just think about what happens to our arctan function as its input tends to positive infinity. So if we draw a quick sketch, let's just say of a graph of y equals tan x, we know that we've got asymptotes when x is pi over 2, and there's also one where x is negative pi over 2, and our tan graph looks like this. And if we were to draw a graph of y equals arctan of x, we now have some horizontal asymptotes. This is where y is equal to pi over 2, and there's also one where y is negative pi over 2. And our arctan graph looks like this. So as x goes to infinity here, you can see that arctan of x is going to tend to pi over 2. So here this is for our graph of y equals arctan of x. So similarly, because k plus 1 times root 3 is tending to infinity, this means that the limit, as this goes to infinity, of arctan k plus 1 root 3 is just going to be pi over 2. So then we can actually conclude then that our original sum is just going to be equal to, first of all, we get pi over 2 for the limit as k goes to infinity of our arctan k plus 1 root 3. So we've got pi over 2, then we take away arctan root 3, which doesn't depend on k. And this is actually a well-known value of arctan. So if you have tan of 60 degrees or you have tan of pi over 3 radians, you get root 3. So the arctan function is defined between minus pi over 2 and positive pi over 2. So this gives us pi over 3 as our value of arctan root 3. So pi over 2 minus pi over 3, this gives us then that our original sum is actually just equal to pi over 6. So now we'll just finish off by exploring in more detail where this identity came from, so it feels like we've proved this in full. So now we do need to be careful with this identity because it doesn't actually hold for all values of x and y. So for example, if you had x was positive root 3 and y was negative root 3, then you could check actually your left-hand side, arctan x minus arctan y, the left-hand side is 2 pi over 3, whereas if we calculate our right-hand side, you end up with arctan of minus root 3, which is going to give us negative pi over 3. So the right-hand side is negative pi over 3, so we're actually off by, there's a difference of pi there. So this doesn't hold for all values of x and y, however, it is going to hold for all values of x and y that we need. So we used x was root 3n plus 1, and y was root 3n, where n was just a positive integer. So now we've got some new information to take in, which we're going to use to help us derive this for certain values of x and y. So first of all, the angle difference formula. This is valid for any values of a and b, so tan a minus b can be written as this fraction. This will be really useful in a moment. And we also need to just consider very carefully what happens if we take a value, let's say z, so we have tan of arctan of z. And this will actually always give us z, because the arctan function has a well-defined inverse. So we take tan of arctan of z, this will always give us z. However, the one where we need to be really careful is doing this the other way round, because the tan function, if you have y equals tan theta, this function isn't invertible, because you could have tan of theta, or you could have tan of theta plus pi, or tan of theta plus 2 pi, and any of these would give you the same output. So when we take arctan of theta plus pi, for example, you would just get theta back, because the arctan function is only defined between minus pi over 2 and pi over 2. So the only outputs that you get are in this range. So if you take a value of theta outside of this range, it will give you, if you do arctan of tan of theta, it will give you something that's in this range, so you don't get the same value back. So this is where we need to be really careful. So our first step in proving this, we'll start with the left-hand side, and we'll actually just take tan of the entire left-hand side, and then we'll show that this is equal to tan of the entire right-hand side. So tan of arctan x minus arctan of y, we can treat these as our a and b in our angle difference formula. So we say this is a and this is b, so regardless of what our values of x and y are, we know that this is always going to be tan a minus tan b over 1 plus tan a tan b. So we can write this now as tan of a, so tan of arctan x, minus tan of arctan y. Then in the denominator are 1 plus tan a tan b, we've got 1 plus tan arctan x times tan of arctan y. So at this point we've got lots of tan of arctan of something, and this is the one where tan of arctan of any value is actually just equal to that value. So here tan of arctan of x is just equal to x, tan of arctan of y is just equal to y, and similarly here the tan and arctans effectively disappear, so we get that tan of our left hand side here is just equal to x minus y over 1 plus x times y, because our tan of arctan of x is just x and our tan of arctan of y terms are just y. So we've shown that tan of the left hand side is equal to x minus y over 1 plus xy, and if we do tan of our right hand side now, then we get tan of arctan of x minus y over 1 plus xy. So then using the same rule as before, we're allowed to do tan of arctan of this fraction. So if we say x minus y over 1 plus xy is our z, this is just equal to itself. So here our tan and arctan cancel when we do them in this order. So this is actually just equal to x minus y over 1 plus xy. So we've shown then, we haven't proven that arctan x minus arctan y is equal to arctan of this fraction, but we have proven that tan of arctan x minus arctan of y is equal to tan of arctan of this fraction, x minus y over 1 plus xy. So we're one step closer to proving this identity for some suitable values of x and y. Now we'd like to somehow get rid of the fact that we've got a tan on both sides of this equation, because what we really want to show is that arctan x minus arctan y is equal to this arctan of this fraction. And to get rid of these tans, you'll notice that so far this is actually true for all values of x and y, which means that we can take arctan of both sides here, and this will still be true for all values of x and y. So if we take arctan of the left-hand side, we've got arctan of tan of arctan x minus arctan y. And similarly on the right-hand side, taking arctan of the right-hand side, we can say for all values of x and y, this is equal to, again, quite a messy looking expression, arctan of tan of arctan of x minus y over 1 plus xy. So here we know that these are equal for all values of x and y, and we'd like to somehow cancel our arctan and our tan here and cancel this arctan and this tan. But unfortunately this doesn't always work, because arctan of tan of theta is equal to theta when theta is between minus pi over 2 and positive pi over 2. So here effectively our theta is arctan x minus arctan y, and the second one, our theta, is effectively arctan x minus y over 1 plus xy. So here we want both of these to be in this range between negative pi over 2 and positive pi over 2, because then we'll be able to cancel our arctan and our tan in each one and prove the identity. So just to summarise what we need then, we want to show that arctan x minus arctan of y, at least for these values of x and y, is between negative pi over 2 and positive pi over 2. And similarly, we want to show that arctan of the fraction x minus y over 1 plus xy is also in this range between minus pi over 2 and positive pi over 2, because then we can just cancel arctan and tan here, because arctan of tan of this theta would just be equal to theta. So our left-hand side reduces to arctan x minus arctan y. This is going to be equal to, on the right-hand side, once again, we'd be able to cancel our arctan and tan if this is between negative pi over 2 and positive pi over 2, and we'd just get arctan of x minus y over 1 plus xy on the right-hand side, at which point the result is proven, at least if this holds for our suitable values of x and y. And to verify that both of these lie within this range between minus pi over 2 and pi over 2, we can just use some simple properties of the arctan function. So if we actually go with the second one to begin with, arctan of anything is going to be between minus pi over 2 and pi over 2. So certainly arctan of x minus y over 1 plus xy is in this range. This is just because our arctan function only takes values in this interval between minus pi over 2 and positive pi over 2. So this is true for any real numbers x and y. So we don't need to worry about this case. However, for arctan of x minus arctan of y, it is possible for certain values of x and y that this doesn't lie in this interval. So earlier we had x was root 3 and y was negative root 3, which would give a value outside of this interval, and this was where our identity didn't work earlier. But fortunately we can just use the fact that x and y being root 3n plus 1 and root 3n, where n is a positive integer, we only need to use the fact that x and y are both positive here. So because x is positive, the arctan function, if you put in a positive input, you'll get a positive output. So this tells us that arctan of x is going to be positive. And alongside the fact that arctan of y just takes values in this interval between minus pi over 2 and pi over 2, we can say that arctan of y then is going to be less than pi over 2. And if we take negatives here, negative arctan of y is going to be greater than negative pi over 2. And this is building up to now we can say that arctan of x is greater than 0, minus arctan of y is greater than minus pi over 2. So combining these, we can say that arctan of x minus arctan of y has got to be greater than 0 plus minus pi over 2, so greater than negative pi over 2. So we've shown then that it's bigger than minus pi over 2, we just need to show that it's less than pi over 2. So similarly, because y is greater than 0, we know that arctan of y is going to be greater than 0, and then taking negatives we get negative arctan of y is going to be less than negative 0, so just less than 0. And once again, just using the fact that arctan of anything is in this interval between minus pi over 2 and pi over 2, arctan of x then has got to be less than pi over 2. So combining these two inequalities then, you see arctan of x minus arctan of y is just going to be less than pi over 2 plus 0, so less than pi over 2. And we've already seen arctan of x minus arctan of y is greater than negative pi over 2. So then we've shown that arctan of x minus arctan of y is in this interval between minus pi over 2 and pi over 2. So both of these conditions are satisfied, which means that our previous argument works and our identity is indeed valid for our values of x and y that we chose, which means then that our sum of this infinite series is indeed pi over 6.